Okay, guys, chalo, we can start now. So I think let's see where were we last time. Martingale, right? So the key property of martingale is said is this. Then we did some examples, and in the end, we were talking about a random walk, right? And we found the probability of a random walk hitting level A before hitting level minus B, and expected time to hit level A or minus B. That came out to be A times B. So now let's look at a random walk as follows. Suppose that xi takes value plus 1 with probability P and minus 1 with probability 1 minus P. Now for this random walk, we want to find the probability that you get level A before you hit level minus B. So how would one proceed typically on this? Give a sense.
xi minus ip. Xi minus ip.
Xi minus the mean.
ip.
You want to get it a martingale like that, basically.
Right.
Right. So you just kind of make it a zero mean thing, and then you go with that. Right. Yeah. No, I was wondering what would be the issue with that. The number of steps are of course going to be random, right? You don't have to worry about time coming in.
So
You will still get something from it, huh?
define ya equals to xi minus.
Yeah, no, I get you. So the mean of this guy is what? C of xi is equal to p minus 1 minus 2, right? I guess. So 1 minus 1, yes, it's equal to 2p minus 1. So you're saying that define y equal to xi minus 2p minus 1
Into. Okay.
This is the mean. This is 0. Right. So then you can say, okay, x times tau, and yes, x tau minus 2p minus 1 tau. So and then you so I will write out. And you know that write out. Look at that E of x tau, which is A into we know the probability of hitting this, and B into the probability of hitting that. We can find. So we don't know the probability very well. No, that's not very clear. Earlier calculation don't quite work. You know, earlier we used two martingales.
So the random martingale y square minus.
Yeah. So those would be two martingales, for example. But I'll give you one martingale which is better, which I know works in the city. And that is that you look at, I guess. Let's see. Sorry. Yeah, it's the same as before, but yeah. Q by P over S. This martingale does the job. So what is the power S? S is equal to summation. Xi is again plus 1 minus 1. This martingale works very well. This turns out to be the right one. But essentially, it's a multiplicative martingale, right? I've just chosen it in such a way that if I look at expected value of Q by P So xi, that's equal to q by p times p plus, I guess, yeah. And then xi takes minus from that direction. P by q times q, that's equal to 1. So it's a martingale with mean one. And now I'm just taking a product of non-negative martingales. A product of mean one with non-negative terms. So this does works very well. Other thing, it's not at all clear to me that you get it with those two martingales. So what's trying to. So with this martingale, okay, now the tau is what it is. So what am I going to do? I'm going to look at 2 by 2. That's tau, right? And that's going to be equal to 1, right? Same argument as before. And S tau can again take only 2 values. That's 2 by P into A into probability that S tau is equal to A, and then plus Q by P to the power minus B into 1 minus probability of S tau. And that has to be zero. Now I can evaluate this probability. It's not good. Let me just take that from roots. So I think it's Q by P to the power B. 1 for yeah. Because that turns out to be.
Isn't this greater than? Isn't this greater than?
So this is when. No, hold on. No, it's not greater. Let's see.
Given less than B is greater than.
So let's see. So if Q is less than P, then both
Okay,
systems are less than 1. You just
yeah.
take negative of both.
Yeah.
If Q is greater than P, then it's greater. Yeah. But you say this that okay, when will this probability be small? It will be small when P is less than Q, right? And then you can say, okay, suppose I want to now I have a random walk with P less than Q. Exercise is a random walk with a negative drift. So I ask myself, okay, what's the charge I hit level A at all? It's always greater than equal to the probability that I hit A before B for any B. And as I let B go to minus infinity to infinity, this probability will converge to the probability that I ever hit A. So I can just take the limit of this as B goes to infinity, and that will turn out to be so I just multiply both the sides by Q by P. P by 2 to A plus B, so I get P by 2 into A plus B plus B by Q to the power A minus 1 or 1 minus B by Q. Again, I'll change. Yeah, no, so P by Q to the power A plus B, right? So I should have like this here, P by Q to the power A plus B. Yeah. So I've tried both, so now this is fine. Okay, and this is okay. Now as I let B go to infinity, this will go to 0 and this will go to 0, right? This will just be to B by 2. Is a limit. Limit as B goes to infinity. E by 2. So it's geometrically can reducing the probability. That's a big insight. This is for a simple random walk. Now you can say, okay, for long random walks, you'd expect this to be true. What's the chance that they hit a large threshold before they go down? So these are in practice used a lot in the insurance settings, loan probabilities. So an insurance company on an app, so we have to extract this problem in the insurance company. Let's see if I can extract it. Yes, this is the way the insurance company usually models things is that the premium is coming at a deterministic rate and the claims are coming at some random time. Okay. And we say interclaim time is IID. Okay. So then suppose after time TI, this is interreliable time between the I minus first and I claim, I want this much premium, CPI. And I saw a claim of size that says CI. Okay. So this is my income. Let me call this as my I. Now these Y is a IID. And
Sir, what is the CI?
so this CI is the claim I have claimed to insurance company. So I'm going to model. So the simplest model, I want to keep it very simple. So my claims are coming in IID. Yes, from some distribution. And the time between two claims is also IID, with some other distribution, TI. So suppose in the time TI, I earn this much premium, C times TI. My premium rate is deterministic. It's a reasonable assumption to make loans 2, 5, 2. And then, so in each, between two claims, I am earning reward of II. Now, typically, if I'm a good insurance company, E by II should be positive. Okay. But still, I'm concerned that although my summation by I should want to n is going to plus infinity, there's a probability that can take a large value. Let me just call minus yi. Let me call this as minus yi. Minus this y is my loss answer. So I expect my losses to go to minus infinity, and I'm worried that my losses can exceed a large threshold. So I'm worried that probability that there exists in n, so that summation yi n is greater or equal to some u. U is a buffer I keep. As an insurance company, from regulation point of view, I'm told to keep certain amount of money u, some crores and crores of rupees. And then I worry that sometimes the claims will be so large that I'll get wiped out. This will happen. So this is basically saying the random walk, which has a negative drift, but nonetheless it will cross a large threshold before it goes down to minus infinity. So this problem is kind of very prototypical in the world of insurance.
What happens? What happens?
The company gets ruined.
No, I do it quickly.
Huh? No. Then that company files bankruptcy. So yeah, it's a complicated process of what you get. What's remaining and what you get. But if you look at histories of many insurance companies, they make money for 30, 40, 50 years, then they get ruined. So it's getting ruined is actually it's probably 1% of this eventually. In the world of finance, each bank is asked to keep certain amount of economic cost of capital or value at risk, so that in the next 2 weeks or so, the probability of it defaulting is less than say 0.1% or 0.01%. So this kind of mathematics, probabilistic mathematics, gets used a lot in the world of finance and insurance. So this is a very basic problem there. It turns out that if your yi is a light tail, so tails become very important in this world. So light tail, I mean, okay, probably the yi here is equal to x is less than or equal to power minus theta x for some theta greater than 0. So exponentially decay. So bounded would of course work. So xi between plus minus 1 what we had fit into this setting. But even if it's light tail, then you will get that these probabilities that I showed you will roughly look like e to the power minus some theta star into 2. So they will be exponentially decaying. which is what we saw right now in our setting. And we saw exact thing, but this is going to be roughly. On the other hand, things become more interesting, and this happens a lot in the world of finance and insurance. That these probabilities are roughly more like 1 upon x bar alpha. So these are fat tails. Fat tails have this very nice property that, well, very nice, very interesting property that. So it's like this. So let me just tell you things. This is a digression for what you're doing. But if you ask Sn greater than equal to u, Sn is just n independent variables. They're all fat tails. Now it looks in the fat tail setting, it looks like this. All these two probabilities, the ratio is 1 to 1. What that means is that the large losses happen, rare event happens because one guy takes a large value. In fact, you can actually argue like this. Let me make this even better. And I just talk about 2 to illustrate the point. So x1 greater than equal to u, given x1 plus x2 greater than equal to u. In the fat tail setting, this probability will converge to 1 by 2, which is the probability that x1 is equal to max. And you said that okay.
These are IIT.
Yeah. And so probably the x1 looks like it's taking value close to x, given x1 plus x2 greater than equal to u, and that will look like 1 by 2 f of x. So meaning with half the probability, x1 behaves like nothing happened. So the way the rate event happens is that one guy takes a massive value and other guys are completely unaware. So claims are coming just like that. So insurance company gets known because there's a massive earthquake, but all the other claims are kind of unchanged. This happens in the heavy tail setting. While in the light tail setting, I think in the exponential setting, it's going to be, if I remember correctly, given x2 equal to u, this looks like I think so it's uniformly distributed. X1 is uniformly distributed between 0 and the light tail setting. And now if you say that, okay, suppose there was a Gaussian tail. Suppose look like e bar minus x squared by 2. Anything which is faster than exponential. Then this will look a lot like close to u by 2 plus small noise. So the rate event happens because all these guys are very close to u by 2. A lot of insight into it. Right? How did the rate event happen? Because all of them kind of have to test themselves to make this event happen. While in the fat tail setting, it's just one guy who kind of had a massive value. I mean, we are basically, there are a variety of ways in which this happens, right? X1 takes value C, X2 takes value U minus C plus some fluff, and you look over all possible C's. So we're looking at all those paths and we're asking which paths are dominant. Where does most of the probability mass lie? And that's what is being captured by this. So in the insurance setting, in the factorial setting, the insurance world. If you were to ask yourself, how does goal happen? It's a very nice expression that you get. What's nice is that it kind of fits in the distribution. So it's like you draw a line, which is the slope of the random walk. It's going in this direction, and in each time there's a probability that one guy takes a value greater than this. So how does the rate event happen? You're going along this line and then suddenly one guy takes this value. Or you're going along this line and suddenly one guy takes this value. Or you're going along this line. You sum all these probabilities up and that's essentially your known probability. That is the same asymptotic. Okay. So, we'll do large integration theory later, and that's going to be about random variables which are exponential tail, which have these exponential movements. The theory when you talk about when the random variables have polynomial tails, this is more under the extreme value theory. Where the very lot more about this kind of stuff. Okay. So now where were we? So we were talking about the martingale and we came up with the expression Q by P. So that's fine. So I think that discussion ends there. Right. Yeah. So now we want to kind of answer this question: expected value of m of tau from martingale, which we stop at a stopping time tau. Up till now, we've seen from some examples that this was equal to E of m of 0. M of 0 can be allowed to be random. Up till now, all of this was true, but is this always true? What can go wrong?
Tau has to be bounded.
What's that?
Tau has to be bounded.
So that's one sufficient condition. So we'll exactly list down some sufficient conditions. I mean, clearly you can do better than just being talking about it. I mean, even in the examples we considered between A and B, tau was not bounded, right?
But we consider the sequence of times tau is.
No. We look at tau minus n. We look at this and we argue that this converges to m of tau. And basically what we needed here was tau was less than infinity. This may not be bounded.
Oh, sorry, almost.
Finite here. But then we use the fact that this was bounded.
Yes.
Yeah. So two things. Because it's going to be in that spirit. We just list those conditions down. Those are the most elegant conditions. Anything else you can work hard and show. It's not very naturally nice condition. But first, let's just talk about some places where things can go wrong. So again, let's look at summation Sn equals summation xi, I equal to 1 to n, and again we have exi equal to 0, xi takes value plus 1, minus 1, and independent. Simple symmetric random. Okay. And now let's define time to be infimum n such that Sn is equal to plus 1. We're taking f0 equal to 0. So first time the simple random walk, it's level 1. That's a stopping time, right? It's clearly a stopping time. And from whatever we know about random walks, we know it's a recurrent Markov chain, right? As I said, that you studied somewhere. Which tells you that, okay, probability that tau is infinity is equal to 1. That you know. Okay. But what can we say about expected value of Sn min tau?
Piece of 0.
0, right? Because it's equal to E of S of 0, 0. Then what can we say about E of S tau, sorry, T? You stop exactly when your Sn is equal to 1. So your St is equal to 1. Right? St is equal to summation Sn indicator that. And you know that this is P is going to stop, it's finite for sure. And every omega will take some finite value. So St is going to be equal to 1 in that. So this is equal to 1. Not equal to CSS. So just making the point that it's not always true that E of St is equal to E of S0. That's not always true. So optional sampling theorem or martingale stopping time theorem is conditions under which it is true. It's very interesting, the longest time I used to worry about adaptive algorithms, where you learn from what you've seen, and then you move forward and you adapt your weights, change whatever the strategy, etc. And it was difficult to, I mean, because you think from first principles, you worry about all the conditionality that you're coming up with. I'm conditioning on this happening, conditioning on that happening. How do I study all this? Turns out the right way to deal with adaptive kind of algorithms is by stopping times and having a martingale and then using martingale stopping time. See, at every step you have a stopping time in what you do, because stopping times are allowed to depend upon the past. They are allowed to be adaptive. And then you have this tool, and it's amazing how far one can go with this kind of analysis. So yeah, tools for also conquering dependence in adaptive algorithms. Through stopping time and through martingale. Often through martingale stopping time. Okay, so what are the conditions? So theorem. Suppose I'll say martingale, but I could say super martingale also. So, this inequality will change, but let me see here. Super martingale is equal to Fn. Now is stopping time. Then E of m tau equal to E of m0. If so, I give something convenience. Okay. And if it's a super martingale, then this becomes less than. Okay. Earlier we had said that okay, n min tau is equal to basically we had said this quantity here was a martingale. If the underlying Markov process was some super martingale, this will also be a super martingale. If the underlying martingale process was a sub martingale, this will also be sub martingale. Because the AIs that we use, remember we had this transform how to construct new martingales from old martingales. If those AIs are non-negative, which they were just indicator functions for us. Then sub martingale remains the sub martingale, super martingale remains super martingale. Nothing really changes. So that's why I won't dwell too much on that. When we need to, we'll see it. Otherwise, cleaner just think of martingales. So if one, okay, tau is less than or equal to k. So this is the boundary case. And this is of course obvious because you have m n min tau is equal to E of m0. Just take n to be greater than equal to k. Still true, right? But then in that case, you know that n min tau is equal to E of tau is equal to tau. So you get this in the this was super clear. Second is okay, we'll just assume that this is true. Right? Now it's no longer bounded with finite. And we'll assume that m n is less equal to y for all n and E of y is less than. Can somebody complete the proof in this setting?
So let the integrator of function.
we've done this.
I say, is it prompted by some?
Okay. So this should tell you that we're going to use dominated interval.
Yeah.
And basically, we go back and say n min tau is dominated by y. See, that's easy to see. And it's converging because tau is finite.
It's almost
So n goes in multi convection and tau. So hence, by dominated convergence theorem, expected value of n min tau converges to e of m tau. But the point is this is always equal to e of m zero. It's always equal to e of m zero. This sequence is converging to this thing. Only way that's going to be true is if this is also equal. So that's the other condition, that the martingale itself is bounded and the stopping time is finite. Now we do one more condition. And that is the increments are less than equal to k. So the increments are bounded. Right? The martingale itself need not be bounded, but the increments are bounded. And E of tau is less than. So this will imply that tau is finite. But now we are asking for more. So we are asking for more here and less there. Right? So these are three conditions to keep in mind. And this is probably the most important one. That the increments themselves are bounded. You see that all the time. And the expected time to stop is finite. So how do we prove this? So you can now see that mn minus m0 is less than or equal to k times n. Okay. Just by triangular inequality. What is it? So m min tau minus m0 less than or equal to k times tau. Okay. So now it's dominated by this, right? And this is converted to the tau. So that's the martingale stopping time theorem. It's not simpler than this. This is set to one more. Basically, we are going to learn in these next few lectures. Martingale is not very powerful. You just see them being used everywhere. On it. But let me ask you a simple question now.
Working on that.
Okay, good to know. But let me state the question on that.
Something went wrong. Please try again.
Okay. This guy I've never spoken to this guy before. Do you ever use this guy city or something? Okay. Anyway, okay. Okay. So you have a monkey typing letters on a keyboard, A, B to Z with equal probability. Okay. Almost time before it does magic, meaning it writes abra, cadabra. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's the expected time till you see the pattern abra, cadabra? We saw a much more complicated discussion of this earlier. Let us see. Huh? Well, expected time. So that would be a reasonable guess, right? 26 to power 11. But so that would actually be true if this last
So
part
it is
here,
KMP you can do, this is basically random walk on the KMP.
on what?
The KMP, what is the longest prefix that currently matches? Yes, then if you delete the adder, then it will be exactly 26. Or if
What's that?
you delete the last adder, it will be exactly.
Yeah. If this last few, any pattern was not matching the first few lines, then indeed it will be 26 to 511. But that's also not an obvious proof, but that also requires some proof. But because it is, in this case, what you get is 26 by 11 plus 26 to the power 4 plus 26. This is going to be expected P. So the question is, one can prove this in a very complicated way, but what's a simpler way of proving it? Now that you know martingale stopping time. So it's a very simple proof, but not an obvious one.
Use it should be what is the longest prefix that currently matches.
What is the longest piece? No, that's true. So that I don't want to use that argument because you're not using martingale, right? So let me give you a martingale argument right now. So I'm going to be at every time monkey types a letter, a game is being played. A martingale is being played. So I'm going to bet 1 rupee. Okay. If I get A, then my 1 rupee becomes 26 rupees. Otherwise, I lose that 1 rupee. So that's how the game happens, the first letter. Similarly, for the second time letter, somebody else starts a game here before seeing the letter. If it's A, that person will get 26 rupees. Otherwise, the person will lose 1 rupee. So we'll continue to play this game until we see the pattern abracadabra. So the number of rupees that are being invested are exactly, if this time taken is T, then the number of rupees that are being invested is exactly T. Now what happens is once A does happen, I get 26 rupees, I don't go home. I put all the 26 rupees in the game on the B. B doesn't happen, I've lost everything. If B does happen, then I put 26 square. I have 26 square rupees now. I put them all for the next letter to happen. Okay. So that's how the game is going on. Now, how much would I have won by this? So the game ends when I see abracadabra, right? So everybody up till now who played this game has lost everything. Only the person who betted here has won, has 26 to about 11 amount of units with him. He sent 1 rupee, but he's got 2611. The person who started the game here, it's nothing on this, right? I have 1, 2, 3, 4, I guess there's CA. 1, 2, 3, 4, 5, 6, 7, 8. So person who started playing here, that guy has won 26 to power 4. And the person who started playing here is 126. And total money that has been invested is minus T. And these are martingales. Every time I'm putting in 1 rupee, it becomes 26 with probability 1 by 26. It becomes 0 with probability 25 by 26. So I'm remaining at level 1 on average. So it's a martingale throughout, right? So expected value, this is going to be equal to 0. So E of T is equal to 26 to the power 11 plus 26 to the power 4 plus 26. So all the proofs that you've seen about this earlier were far, far more complicated than this. Right?
Can you explain 26 to the power 4?
Well, at the time of stopping here, when I stopped after I saw abracadabra, because this last A came, right? Then the guy who put 1 rupee just before this A, he got 26 rupees.
Yes.
Okay. The guy who started putting 1 rupee here, his wealth right now is 26 to the power 4. Because he put 1 rupee, he saw A, it became 26. He put 26 in, B came, it became 26 square. He put 26 square in, R came. So he is winning 26 to the power 4. This guy is winning 26. I mean, he has 26 to the power 4 amount in his hand. This guy has 26 in his hand. This guy has 26 to the power 11 in his hand. And everybody has paid 1 rupee up till now.
That's why publishers they counting the 26 and for the stocks token.
What's that? Yeah. So the total amount that has been given to the system is T. And total of money that people have won is T people have won money. This guy has a total wealth of 26 by 11 in his hand right now. So when he's won 26 by 11 minus 1, 26 by 4 minus 1, 26. The total wealth that they have is this. Total amount that has been spent is T. But this is each increment is a zero mean thing. If I win something, I lose something on average, I'm gaining 0 rupees. So it's still a martingale, so DFT you do. You can formalize it and say, okay, give notation to it. So one guy starts here, one martingale, second guy starts here, another martingale. Once they stop, they leave. So we sum up all these martingales, that's still a martingale. Sum of martingales is still a martingale.
Why didn't they cannot start from C or like why they complete your 4? Why is it starting from-
Well, I start from the first, from here, before the game, but the whole monkey types the first letter. One guy puts in 1 rupee. If the letter comes out to be A, that guy will be getting 25 rupees from the system, he'll have 26 rupees with it. If the letter comes out to be something else, probably 25 by 26, he'll lose 1 rupee. So he'll win 25 rupees with probability 1 by 26, and he'll lose 1 rupee with probability.
Like each player is like getting that your word is coming to be advertised.
Yeah,
So that's why-
yeah. And once you see an A, then whatever you have with the 26 rupees, you put on B. And if B also comes, then you put 26 square on R, and so on and so forth. Very neat, huh? Now you can do all of these problems. So you can see the power of martingales. It will do all kinds of funky things very quickly. And we'll keep seeing this. Okay, so this is martingale stopping time influence. Now let's do big result, martingale emergency. So suppose Mn is a martingale, I'll hide the filtration with some martingale. Suppose it's L1 bounded. Okay. The theorem implies that there exists an infinity random variable such that Mn converges to M infinity almost surely. And M infinity is in alpha, meaning expected value of absolute value of infinity is finite. That's a theorem. Okay, so this is nice. And It's again, in terms of beauty, it's hard to come up with a nicer proof than what we have right now. Than for this. More intuitive proof. For something as interesting as this, as general as this. So let's look at this. Let's look at a set where we don't have convergence. What does that mean? Omega says that lim inf mn is less than lim super. Right? That's a set where we don't have convergence. Otherwise, lim inf is equal to lim sup. They could be plus infinity, they could be minus infinity, but we have convergence. Okay? On an extended random variable sense. So this must be true, right? This is a subset of omega such that limit mn is less than a, is less than b, is less than lim sup mn union over a and b both are rational. Okay. Because whenever lim inf differs from lim sup, there must be two rationals in between. And rationals are countable, that's the main.
Like, it must be equal, right? Like the two sides.
That's. But I don't need to nitpick right now. I mean, the thing is, because it's countable, if I can just show that each of these sets has probability 0, then the union also has probability 0. That's what makes my life much easier. So all I need to show to you is they're all done by do.
So you're using the fact that countable union of measure 0 sets is
We've been using it all the time.
general particular.
When we say xn converges to x almost surely, then you know. Use xn will they're also used. Yeah. So we basically, so what I need to show you is this. So let me call that set as HEB. Okay. So I just need to show you the probability of HAB is equal to 0. So if I show you this random, then this will follow the old union will have probability 0, and I'll then I will have convergence. Then my m infinity can simply be taken to be okay. So once I show this, then I'm in business. Sort of you look confused. I have the effect. I had the effect of this.
No, I get it.
Okay, well, whatever we can do to help. Dakshin massage you.
No.
You're missing your comments otherwise. Okay, so m infinity is this. So now we want to, so you can see, for example, that E of, so if we can show this, then we want to claim that this is going to be less than this. Okay. And we know that Mn is converging to an infinity function, which of course means that absolute value this will also converge. Right? So why is this true? Whatever you know right now. Assuming this is true, why is this true?
So if case A means is less than some absolute constant K, that means the limit will also be less than absolute constant.
Say again?
I think each of these universe supremum of E of n is
Okay,
less than 2.
that's a great point that we know this thing.
Absolutely. Okay. So I it's less than some constant.
Yeah, so it's less than infinity, so it's equal to some percent k.
So by dominated power just
No, but dominator requires one variable, right?
oh,
Yeah, so that won't quite work. And you're right that each of these guys is less than some constant k. Oh, I see. But no, well, that still doesn't work because you
so
want
can you say each n is pointwise counted by some.
that because that need not be true. All we know is the expected value of the function. But do you agree that, so I'll tell you now you know.
Status.
Huh?
Status.
Very nice, yeah. But this implies that limit E of mn is an infinity. And this and that's equal to E of just from Fatussila. We need this to be non-negative. Fatussila. Okay. Right. So good. So all we need to show is probability of HAB is equal to 0. Everything else is kind of just falling in our laps. This is a set where n and u sub are between A and B. So let me define random variable u n A and B. This is number of times my martingale goes from below A to above B in n steps.
Do you mean each side less than a and each side plus 1 greater?
No, I mean the subsequence, so that at some point you're less than A, thereafter you're less than above B, some point you're less than A, then thereafter you're less than A. So the largest case such that we have n I, let's say 1 is less than A, n I 2 is it's actually. So I'm going to need some more notation, but let me just say what I want to say. We can accept that we don't have to be that precise. Mi2 is greater than B. Mi3 is less than A. Mi4 is less than B. Mi K is less than A. Minus 1. I K is. So I want to find a subsequence, largest subsequence from between 1 to n with this property.
K or okay.
So what's the question?
So is it supposed to be K or 2K?
Yeah, that's what I'm saying. So I'll have to divide by 2 x, yeah. To be precise, yeah. Yeah, so I was wondering how to write this largest case so that it's true that I want to have kind of 2k here. So maybe you're right, maybe I should just call it as 2k. Let this be 2k next one. That would be accurate. Right?
And this I 2K is
Yeah. So largest k is this one. Okay, and that I'm calling as U and A. These are the process. CSS I can log this in this, no? It can be 0, we never have no of course. In n steps, you look at your path of M1 and M2 and M3. But look over, let's just see. This is your level A, this is your level B. Your M1 can be here. You know, this is your 1, 2, 3, 4. And you could never come to these guys, then it's 0. Or you can sometimes come here, then go, and then stay here, then it's 1. Or maybe you can come down and then go back up, then it's 2.
Yes.
So it always exists, right?
It's largest.
Yeah, I mean, it's in amongst finitely many subsequences. Maximum amongst finite number of every subsequence.
The number of sections.
Yeah, number. I mean, yeah, maybe it's largest case is it's writing in a particular manner, but all we really mean is let's say draw a picture and count the number of times you go from here. Let's not miss anything. That in that sense we mean the largest. I can only come up with the subsequence where I miss sometimes that jump. So I don't want to do that. By including everything that I get. Okay, so let's see what are we going to do. So let's suppose that M1 is here, and then we go maybe here, then we go here, then we go here. Something like this, let's say. Just some arbitrary sample path. So this is omega by omega, right? So I'm going to create a new martingale, which is going to basically so whenever I'm below A, I will count the value until I cross B. This B. Once I cross B, I stop counting these things. These I make them as dash lines. And I stop counting until I come down below A again. And then I again start playing the game. It's like I'm playing a game. So I start betting when I'm below A. First time I'm below A, I start betting until I've crossed B. And once I've crossed B, I stop betting until I come down below A. And then I start betting again. And then I keep on betting until I cross B, and so on and so forth. Is this clear? This is a game I'm going to play. So what am I doing? I'm looking at this new process. Let me define C0 is equal to, this is C1 is equal to indicator that M1 is less than A. See, if M1 is less than A, then I'm playing the game. M0. So C1 should be F0 adaptable. And Cn is going to be, suppose I'm already playing a game. So Cn minus 1 is equal to 1. So I'm playing the game and I'm not, the last step I'm not crossed B. So I continue to play the game. Or I'm not playing the game. And last time I become less than B. So then again I start playing. So this is exactly capturing what I just said earlier. Okay, so now my winnings with this is going to be another martingale, which is, so my winning is going to be by n, which is equal to summation Cn m minus n minus 1. It's 1 to n. Okay. Now you can see that C1 was a pre-visible process. non-anticipated, and inductively so is Cn. If Cn minus 1 is certainly Fn minus 1 measurable, this is Fn minus measurable, so on. So my Cn process is pre-visible, so this is a proper martingale. Means zero martingale. And sub-martingale and super martingale is my original process of the super martingale. Okay. So what's nice about this is actually counting, it becomes active once I come below A, and then it remains active till I cross B. So I can say that my yn is greater than or equal to number of times I cross A and B times B minus A. But I have to worry about something. Towards the end, I'm playing a game here. Okay, I'm not crossed. So I have, I started playing the game from this point onwards. This was passion, right? Suppose I'm not playing here. And this point is A, and this point is xn. So I have this much amount to worry about, this A minus xn, the positive part. So I should have minus A minus xn, the positive. Now I have it. So my yn, this summation, it has to worry about the last piece also, right? But the last piece can at most be this much. Otherwise, I get this inequality. That's all I really need. I've done that. This is where the probabilistic algorithm is. So now, what can I say about expected value of yn? It's a super martingale, so it's non-negative. Yeah, it's less than or equal to 0. In martingale setting, it's equal to 0. So I'm going to assume that this is expected value of UNAV B minus A minus expected value of A minus xn, the positive part. Okay, now can somebody complete the overall picture? I claim the agreement done.
The E of UN minus E of UN AB is less than or equal to E of A minus xn plus y minus. And E of A minus xn plus goes to 0.
No, it's not going to 0. It just has to be finite. It just has to be bounded. Okay, all I need to prove is E of UN is going to converge to So UN AB. It's a non-decreasing random variable which is increasing with x is going to converge to E of U infinity AB, right? If I can show that this is bounded, that tells me that probability that U infinity AB is less than infinity is equal to 1. Only then will this expected value be finite. And when this is less than infinity, then you said HAB will have probability 0. Yeah. Because if in HAB your limit was below and lim sup was above, that means you are going from above to below infinity many times. So this tells you that you can't do that. So that's all you really need. E of this is less than, so E of A minus xn, that you can just upper bound by xn is mn. Yeah. Right. So this is bounded. So this term here is bounded. So as n goes to infinity, EU infinity is bounded. This is infinity. So that's a martingale condition. Right. So it's good that in all these measure theoretic arguments where you're taking care of these, there's still geometric intuition to be had. You can say kind of very interesting things. Right. But still connecting a lot of things in a very nice manner. Interesting stuff. So now there's a question here. Is expected value of m infinity which exists, is it equal to e of m0? Or is it less than equal to e of m0 depending on in the super martingale set? Right? I guess it's, yeah, we've not really proved that. So it turns out that you could have cases where e of m infinity is actually only b. So what I'm saying is we have m infinity, mn is converging to m infinity. And I guess the question is, sorry. So the question I'm asking is it true that e of mn is converging to e of m infinity? That's right. Is this true?
So if E of infinity is less than infinity, doesn't this follow by
M infinity is not, I mean, all we've said so far is that, okay, e of m infinity is less than or equal to sup m e of m.
you don't know E of mod A.
Yeah.
We also need it to be pointwise.
Remember, even for, I'll just complete the sentence, that even to get uniform integrability, this was not enough. We needed, okay, 1 plus epsilon of this. If this was finite, then we would have got uniform integrability. And then this would have fallen. So we don't have that yet. Is your point?
Like, we need the sequence element to be pointwise bounded, then we can apply this.
Yeah, we need point by random variable, which is integrable. Then it can. Yeah, so this need not be true. I'll give you one example. I could have given you an easy example, but I'll give you a fun example. Because that way we get to see the theory of branching processes a little bit. It comes up with branching process theory. And that's again a very nice theory. So I'll just discuss that for the next 12 minutes. You heard of branching processes so far or in any context? You have. It's a nice kind of a basic model for population, how population grows. And certainly it also can be a model for how the virus spreads in early on. So you start with say population of person. And the one person will have, let's say, Z1 offspring. Or Z1 offspring in generation 1, let's say. So this has some probability distribution. Probability distribution same with that, let's call it the generic analysis of Z. And we assume that probability that Z equal to 0 is greater than 0. Right? There is some chance that a person will not have an offspring. Okay. And now what's the story is possible? X0 is going to, after one time unit, it will die out and will have Z offsprings. Random number. And then those Z offsprings will have separately Zi offsprings, IID, with the same distribution. And then this process will continue. So it's a branching tree.
Then your parents die out.
Yeah, each time per parent dies out. So I have these many offsprings, and this guy has some offsprings, he has some offsprings. So forth. And what happens with this tree? That's the question. So it's population evolution, and what happens with this population as time goes to infinity? Does it explode or does it die out? And as I mentioned, it gives a lot of insight also into the COVID kind of behavior. This R naught that we heard about and all that stuff. It's kind of related to this one.
But yet the person does not die out.
What's that?
The person does not die out. I mean, does not get infected.
Either you will die out or you will get COVID like that. It's either
And
one.
then it's-
Susceptible, infected.
The point is the virus doesn't really die.
No, no, I mean, you're saying the parent dies in the reloaded instant.
Yeah.
That does not.
Yeah, no, it's a model in that sense, right? Yeah, after one time period, no, in the sense the person who's got infected recovers. So in that sense, the virus in that person died out. And that person before recovering infected some random number of people. That's the number of children. So people are, it dies out one way or the other. Either person himself dies
Yeah.
or the person recovers. Yeah, but infection stops from that person. Okay, so it's a very nice question to ask and a very nice model. This goes back to Francis Galton, who was, have you heard that name before at all? Or? I'm saying this story yesterday. So this is, he was actually Darwin's cousin, and I guess influenced by Darwin's theory. But he was very much interested in eugenics, study of genes basically, but also kind of claiming that some people have superior genes over some other, or some races have superior genes over others. So very dangerous stuff. This is late 19th century, and presumably these kind of ideas played a role in Europe, going to Second World War. So in that sense, yeah, his history is mixed. But he came up with very nice devices, I think the idea of bell curve comes from him. IQ has a bell curve distribution, etc. But he kind of had this devices where he takes these balls and throws them through some device. So they have equal chance of going to any of these different pockets. Have you seen that? He throws lots of them and then it looks like it makes a bell curve. Galton board, yeah, exactly. So he came up with that board, yeah. Just to illustrate central limit theorem graphically. So I think, yeah, he probably was the first one to formulate branching processes. I need to confirm that fact. Okay, so now the question is, okay. So let's study this branching process for a while. So what are we going to do? So we have xn, population size at time n. Assume that xn minus 1 is greater than 0. Because once xn is 0, then you're stuck to 0. So then this is going to be zi n minus 1 I equal 1 to xn minus 1.
What is X?
This is population size at nth time period. And that's population size at n minus first time period. Okay.
This eraser.
Hmm?
This eraser.
Yeah, exactly. Yeah. So now you can see that, okay, this is a e of xn given xn minus 1. Conditional expectation is this. Let's say e of zi, e of z is equal to mu. This is equal to mu into xn minus 1. Right. So in particular, you can say that, okay, what can you say? Yeah, that is true. I wanted to say that x, yeah, no, I guess you can say that xn by mu, and I won't use that fact right now. Is a martingale.
Xn by mu.
Huh?
Well, xn by mu.
Xn by mu to power n. ठीक है ना? If I divide this by mu to power n, then I get mu to power
Xn
n.
by mu. Okay. Xn by mu.
Not whole power. Just Xn.
Oh yeah. Sorry. This is right. Okay. Yeah. And it's a non-negative martingale. Because it's non-negative martingale, it's L1 bounded. Right? Because each mean is constant. So expected value of xn by mu to power n is equal to 1, right? X equal to x0 basically. X0, let's assume x0 is 1. For all n. So that means xn by mu to the power n is converting to some x infinity. One more show. So that tells you okay that this guy also can behave. That xn looks a lot like mu to the power n x infinity. Okay. That tells you okay, certainly xn is going to 0, mu is less than 1.
Yeah.
And that just follows from here. So the population will manage to show if mu is less than 1. That's what we say that nowadays, like in Europe, the fertility rates are less than 1. For a couple, less than 2. So.
Actually, why is it just E of xn equals to e power n from this above expression?
Same thing here.
You said okay.
You know, this is just using marking calculation.
Yes.
So we're saying something more now. Okay. So I want to say this, what do I want to say here? Suppose mu is equal to 1. Then I have xn is converting to x infinity. And I want to say that x infinity is 0. If mu is equal to 1, if we are in stable setting, each person has exactly 1 replacement on average, eventually population will die. That's an interesting result, right? Yeah, so I want to say x infinity is equal to 0. Meaning eventually population dies out. That's what I want to say. Then because if population dies out, then x, so I guess probability that xn is equal to 0 for some n. That should be equal to 1. But that will mean that xn is equal to 0 thereafter. And hence x infinity is equal to 0. But let's call this probability as pi 0. This is the probability that population goes extinct. So it's interesting that this pi 0 is going to be between 0 and 1 if mu is greater than 1. And it's going to be equal to 1 if mu is less than or equal to 1. So that's what we want to say. And it's not such a straightforward argument like this. So I have one argument. It's nice enough argument. Let me take it here. Okay. So let's look at f of theta. This transform theta to power z. So it's a transform. I mean, I'm not calling it e to power log of theta to power z. I'm calling it e to power theta to power z. That's just there's a reason for that, I guess. Doing it right now. Messing up somewhere. Then I said, no, actually, let me call it this. As n of theta. Let me call this as xn. It's a transform of population at time n. Then I know that S n of theta is equal to part theta into summation zi I equal to 1 to xn. Right? When xn minus 1 is 0, then this is 0. Like this. This is going to be equal to e to power theta zi. So if I just look at xn minus 1, so expected value, right? This is equal to Sn of F theta is equal to F1 theta. Fn minus 1. And F theta is equal to C. So now I can recurse on this, right? Fn minus 1. Or I can just go F into Fn of F. Probably using that notation. I just want to say it's a composition F times 10 times. So this F is one if 10 times. Right. What do I know about Fn theta? Fn1. When theta is equal to 1. Right? That's equal to it's going to be when xn is 0.
So here times means the first one is
I
equal.
have to look at my notes. Sorry.
There times means the first one is F1, then F2 and so on.
No, they're all the same. They're all the same. So I've Fn minus 1, I've written as Fn minus 2. Okay. F of F, Fn minus 3, F of F. So I've got another. Okay, now this is. Sorry. If I had something else. No. So F1 is of course equal to 1, and 1 of course. But if I look at Fn prime theta, that's equal to Xn into log theta, right? D by d theta of that. And d by d theta and expectation can be replaced when the function is continuous. You need to prove that, because this is again interchange of limit and integration. But it can be done, so this will come inside. And then what do I get? Even if I could just get it there, yeah, so I don't need to do this. So this is going to be theta bar xn into theta bar xn minus 1, right? And that means Fn prime 1 is equal to theta bar xn. So and this is equal to 1 when mu is equal to 1. I'm considering the case mu equal to 1. That's what interesting. So then I have Fn1 and Fn prime 1 is equal to both are equal to 1. And I have Fn0. That's equal to 0. So that's actually equal to probability of extent. Need to now write one equation check on second number. Yeah. Let me define. Let's call this as pi of n. Pi of n is the probability that the population has vanished by time n. So pi n plus 1. F n plus 1 0, and that's just equal to f n of f of 0, right? Yeah. Or f of f n of 0. So it's equal to f of pi is equal to pi.
Taking the
And now I know that this pi n is increasing to some pi. You know, once the population becomes extinct, it remains extinct. So that tells me that this is going to, because f is a continuous function, so this equation will be true. That's why we're doing all this. That this pi must satisfy pi to the pi. So now, okay, I have this picture of my f. F0 is probably at z is equal to 0. It's positive. This is my x here, this is my f of x. This is 45-degree line. I know my at point 1, I need my f of 1 to be equal to 1 and f prime 1 to be equal to 1. And you can see that f is actually non-decreasing function, f theta. So f theta is equal to expected value of theta plus c. Right? I'm just saying x0 is equal to 1. So you can actually check that this is going to be a convex function. How do we see that? Yeah, let me check that. F prime theta is equal to this.
and all this computers all
Right, so it's going to be. So for theta greater than 0, it's a non-negative function. It's convex.
It has to be Z, does not respond.
Z. Even then, theta is positive. Theta is between 0 and 1. Still g squared into theta is just so I'm looking for a convex function which starts from somewhere here, and it has to be like this. It can't be function like this. Because if it was in the slope at this point, will be bigger than 45 degrees. And we know that the slope is actually going to be increasing, and slope is equal to 1 at this point. So it can't be equal to 1 earlier. There's only one solution to this pi to that pi, that's pi equal to 1. So it's a very long answer to the problem that probability of getting extent is equal to 1 when your mu is equal to 1.
and to ready 1 plus epsilon is not
Yeah, then it'll be less, then it'll be this guy. This one. Then it'll be like this.
it is either 0 or 1.
No. It'll be positive. It'll start from here. Pi equal to pi epsilon should be true.
Okay.
So it'll be this one. Okay, so how are we doing on time? Yeah. So this is the point, and the point of all this was that, okay, now you have, in this case, we show that E of xn is equal to E of x0, which is equal to 1, but xn is converging to x infinity, and x infinity is equal to 0 on the show. So xn is a martingale. E of xn is always equal to 1, but it's converging to something which in the limit is equal to 0. It's a nice example, I guess. Yeah. So yeah, so it's been this could have been become more clear, but you can see this is the first chapter discussion from David Williams. So he talked about all this. Okay, so now I'm going to assume that you know Martingale-Stockington theorem. I can give you some homework also right before the exam. Okay, so Let me do that today. And you know,
So many channels. Homework.
it's at next Wednesday, right? So this exam we are scheduling for 2 weeks from now, right? And right. And we set Tuesday. Now we have this one day of Tuesday will be, there's lots that happens on Tuesdays. Okay, let's aim for Tuesday. You know, so Tuesday 2 weeks from now. That's what the exam is. But let me give you some homework on martingale exam. Okay? So you get some practice. Okay. Any questions? There.